Hello everyone. So this is a question from JEE Mains 2026, 21st Jan morning. So the question is, for the reaction N2O4 reversible to NO2, graph is plotted as shown below. So this is the graph that they have given. Okay. Identify the correct statements. Okay. So there are some statements given to us. So we'll look at them one by one. Chapters involve thermodynamics, equilibrium, and this is the graph. Okay. So in this graph, we can see in the y-axis we have G, and that is the Gibbs free energy, and in the x-axis we have fraction of N2O4 dissociated. Okay, and also we can see that the graph has a minima, okay, at this particular fraction. So we'll understand what does this minima mean, yeah, denote, and also some values are given to us. Okay. So before we proceed, we need to understand few things about, what's the difference between these things, that is A becoming B, or A irreversible reaction becoming B, B irreversible reaction becoming A reversible reaction to form B, B reversible reaction to form A. So there is a huge difference between these four things. We need to understand the difference. The first one means that that we have pure A, only pure A. We started with 100% A, and after a certain period of time, we get 100% of B. Okay, after some time we get, that time is not specified by thermodynamics. It's a department of kinetics. But what we can say is, after a particular interval of time, we get 100% of B. Same thing applies here also. We start with 100% of B. Okay, and this is irreversible. So that's why we get 100%. We started with 100% A. We are getting 100% B. Similarly here, we start with 100% of B. After a time interval, we'll be having, in the reaction mixture, we'll be having only 100% of A. That's it. Okay, but there is a huge difference in these two cases. Okay, so when I write A reversible reaction to form B, so this also means that okay, we are starting with 100% of A. There is no doubt about it that we start with 100% of A. Okay, and if you know that when you have huge number of atoms, huge concentration of A, the forward reaction will be very high. So initially the forward reaction is very high. Forward reaction very high. Why? Because we have all of them as A. So after some time, what's going to happen? Slowly the amount of B is going to increase, because the forward reaction is happening now. So slowly the backward reaction starts to happen, and after an amount of A has reacted, okay, and after an amount of A has reacted, rate of forward becomes equal to rate of backward, or we can say we reached equilibrium, we arrived at equilibrium. And the moment we reach equilibrium, the concentration of equilibrium mixture does not change. Okay, so what is happening here? Initially you started with A, 100% A, and there was nothing of B, obviously. Then initially the forward reaction will be very high because you have everything of A. And after some time, what is happening? The forward reaction starts to happen, and we start getting some amount of B. And after some amount of B has formed, that B will also start reacting or to become A, because this is reversible. Forward as well as backward can happen. Initially forward reaction very high, slowly the backward reaction will pick up, and after some time what will happen? The rate of forward will be equal to rate of backward. And that point we say that we have reached equilibrium, and we know that after we have reached equilibrium, the concentration of equilibrium mixture does not change. So what is actually happening? We start with 100% of A, and we go and reach only to equilibrium mixture which consists of both A and B. That is the journey of this reaction, right? That is the journey of the reaction. We don't actually get 100% of B because this is a reversible reaction, right? Same thing applies in this case also. So that is B and A. So we start with 100% of B, and our journey is, the final destination is, we reach to an equilibrium mixture of A and B. Okay, that is the difference between a reversible reaction and an irreversible reaction. Okay, so that's what we need to know. Okay, cool. Now we know few points, so let's understand few things. That, for example, we know that a reaction is spontaneous if a reaction is spontaneous if delta G is negative, right? So in a reversible reaction, forward as well as backward reaction happens. So what does that mean? So therefore delta G is negative for forward as well as backward reaction. So therefore for a reversible reaction, delta G is negative for forward as well as backward reaction. We'll see how. How is it possible? Okay. So let us consider a reaction N2O4 giving us 2 moles of NO2. Okay. So we need to calculate the delta G naught, delta R G naught for this. So when we say delta R G naught, what does that mean? That means G naught of products minus G naught of reactants. Okay. So what we do is, so that is technically G naught of 2 moles of NO2 minus G naught of N2O4. This is what they are asking us to calculate, delta R G naught, right? So for this we have to go back and look at the graph. So this is our graph. So can you see, this is the G of 1 mole of N2O4, and this is the G of 2 moles of NO2, that is Gibbs free energy of 2 moles of NO2, right? So what's the difference between them? So can you see this GB is greater, obviously, and GA is smaller, so the difference between them is 5.4, right? So the delta R G naught, or the Gibbs free the change in Gibbs free energy of the reaction, so that is plus 5.4 kilojoules per mole. That is correct. Okay, so if we go according to this, so which reaction I'm talking about? This reaction N2O4 giving rise to 2NO2, right? So this we have calculated assuming that N2O4 completely dissociates into 2NO2. That's why we have subtracted 2NO2 minus N2O4, right? Whenever we have to calculate delta G naught of the reaction, we assume that the reactants have totally become the products. That's why we are getting it as plus 5.4, right? And this value is kind of misleading. Okay, I will explain how is it misleading. So since the delta R G naught is positive, right? So therefore the N2O4 should not dissociate at all. Should not dissociate into NO2. So there is the first misconception. And the second misconception is that reverse reaction would go to completion. Okay, what is the reverse reaction? That is 2NO2 reversible to N2O4, right? So if we calculate the delta R G naught for this reaction, so that will be G of products, that is N2O4 minus G of 2 moles of NO2. So this will come out to be minus of 5.4. So you might think that, okay, since the delta R G naught value is minus of 5.4, so this 2 moles of NO2 will completely become N2O4. That's not going to happen. So that's why I told you that delta R G naught values are kind of misleading. Why are they misleading? Because this is a reversible reaction. This is talking about a irreversible reaction. Delta R G naught is assuming that the product or the reactant completely becomes the product. But this doesn't happen here because this is a this is a reversible reaction which approaches equilibrium. Okay, so here the first statement, that is delta R G naught is positive, so N2O4 should not dissociate into NO2. That's not correct, because again I will emphasize on this point that delta R G naught is calculated assuming that reactants completely convert into products, but that's not the case here. Here the reactant is converting into an equilibrium mixture, as we have discussed. Okay, same thing applies here. The reverse reaction would go to completion, so we calculated the delta R G naught for this reverse reaction. Again, when we calculate delta R G naught, we assume that the reactant has become product. That's not the scene in reversible reactions. In reversible reactions, the reactant becomes a equilibrium mixture. Okay, so therefore these values are misleading. Just because delta R, this is calculated assuming that this converts completely into this. Okay, so therefore both these statements are not correct. Both these statements are not correct. Okay, so what is the correct statement? Since the reaction is reversible, therefore it tends to go to equilibrium, not to completion, and forward as well as backward reaction are spontaneous. Okay, so the problem with calculating delta R G naught for these reactions, that is N2O4 giving rise to 2NO2, is that it is assuming that the final destination of the reaction is, the reactants became products. No, just now we have discussed that in a reversible reaction, 100% of the reactant becomes a equilibrium mixture. So therefore, our final destination point should be the equilibrium mixture, not the 100% product. Okay, that's an important thing that delta R G naught does not consider. Okay, now we will look into the graph. Okay, the graph is really important to us. Yeah. Okay, so A is, the standard free energy of 1 mole of N2O4. B is standard free energy of 2 moles of NO2. And the other points between A and B, any point here, any point is the free energy of mixtures of N2O4 and NO2. I mean, any other point is the free energy of mixture containing both N2O4 and NO2. Because if you remember, in equilibrium, we have mixtures of both N2O4 and NO2, right? One more thing, free energy curve has a minimum at this point, right? This is the point, and this point is the equilibrium point. And if I draw a line here, this is the fraction of, let's say this is, this will be around 16%. So that means the equilibrium fraction contains 16% of N2O4, or sorry, the 16% of N2O4 has dissociated in the equilibrium mixture. So this is the equilibrium mixture. Okay, so we start from A, but we end up in this, we start from A, 100% of A, but at equilibrium we end up with 16% of N2O4 getting dissociated. So this is the final destination. In delta R G naught, we are assuming that, okay, we start with this, we end here. No, that doesn't happen. Okay, so for the reaction, delta G naught for the reaction is going to be, delta R G naught for the reaction is going to be obviously G of product minus G of reactant, because we are assuming that okay, A completely becomes B, or you can say the reactants completely become products. So the G of product is 5.4, G of reactant is so product minus reactant, so this value is 5.4, correct? So this is 5.4, right? But there is one observation. The observation is free energy of the reaction mixture is less than either of the pure reactant A or the product B. Can you see that? Free energy of, this is the equilibrium mixture, is less than pure reactant A as well as the pure product B. Okay, so now so we have to calculate when 1 mole of N2O4 changes into equilibrium mixture. So what will be the delta G naught value? So delta G naught is always the destination that we have reached minus what we have started with. So obviously G of the equilibrium mixture minus G of N2O4 that we started with, 1 mole of N2O4. Okay, so G of the equilibrium mixture is, this is 0 minus 1 mole of N2O4, that is okay. So from the graph, can you see that this difference is 0.84, and so therefore G of A is going to be 0.84. So therefore delta G naught is minus 0.84. So can you see a negative value, right? So since the delta G naught of change from 1 mole of A into the reaction mixture is negative, so therefore forward reaction is spontaneous. Okay, then when we have 2 moles of NO2 changes into equilibrium mixture, so delta G naught, how will we calculate? So obviously 2 moles of NO2 is changing into equilibrium mixture, so it will be G of equilibrium mixture minus G of 2 moles of NO2, right? So G of equilibrium mixture is 0, and G of 2 moles of NO2 is, can you see, this is the 0, and this value will be, so this value will be 0.84 plus 5.4, right? Again I will represent here, this is the 0 of the curve, so this value will be 0.84 plus 5.4. Okay, so 0 minus 0.84 plus 5.4, so this value comes out to be minus 6.24. Okay, so therefore can you see for the backward reaction also, that is when we started with 2 moles of NO2 and when we form the equilibrium mixture ultimately, for that also delta G naught is coming out to be negative. So that's what I mean when I said that for the reversible reaction delta G is negative for forward as well as backward reaction. Okay, that's what I mean, because in both the cases, when 1 mole of N2O4 is becoming the equilibrium mixture or the forward reaction, delta G naught is minus 0.84. When 2 moles of NO2 changes into equilibrium mixture, that is the backward reaction, for that also delta G naught is minus 6.24. Okay, so in both the cases delta G naught is, in both cases delta G naught is negative, so therefore forward as well as backward reaction is spontaneous. Okay, till the moment they reach the equilibrium mixture. Okay, so let us look into the options. So first option, standard free energy change for the reaction is minus 5.4. No, because for the standard free energy change for the reaction will be, so from the graph, so they are asking delta RG naught, so that is always product, that is, so assume that A is becoming B. So to calculate for the reaction, assume that A has completely become B, so it will be G of B minus G of A, right? So product is higher and this is the reactant, so this minus this is going to be plus 5.4 plus 5.4, not minus. Okay, so this is a wrong statement. Second, as delta G naught in graph is positive, yes, N2O4 will not dissociate into NO2 at all. This is, again, I told you that yes, the delta G naught is plus 5.4, but that is assuming that A completely becomes B, but that doesn't happen. A usually, A becomes into a equilibrium mixture of A and B because this is a reversible reaction. Okay, so therefore for this to happen, let us calculate the delta G for this to happen. So it will be G of equilibrium mixture minus G of A. So G of equilibrium mixture is 0, G of A is, we know it is 0.84. So Can you see this is a negative value? So that means this is a spontaneous reaction. That is, A becoming into equilibrium mixture is a spontaneous reaction. So it will happen. Okay, it's going to happen. So this is again a wrong statement. Then third, reverse reaction will go to completion, right? So what is the reverse reaction? Reverse reaction is, B becoming A. This is the reverse reaction. Okay, so B is obviously 2 moles of NO2 and A is N2O4, right? So if we calculate the delta G for this, so it will be G of N2O4 minus G of 2 moles of NO2, right? So can you see that value will be N2O4? So it will be this value minus this value, smaller minus bigger. That's why it will be minus 5.4, right? Minus 5.4. So this tells us that okay, every amount of B will convert into A. That is not going to happen because this reaction is a reversible reaction. So instead, 2NO2, that is 2 moles of NO2, converts into an equilibrium mixture, right? So therefore, it does not go to completion. It goes into an equilibrium mixture. Okay, cool. So this statement is also correct. Let us look at option D. When 1 mole of N2O4 changes into equilibrium mixture, value of delta G naught is minus 0.84. We just calculated that equilibrium mixture minus GA, that is minus 0.84. Correct. This statement is correct. And the final one, when 2 mole of NO2 changes into equilibrium mixture, delta G naught for equilibrium mixture is minus 6.24. Okay. So how to calculate that? Okay, so assume that 2 moles of NO2 is becoming equilibrium mixture. So delta G for this will be final minus initial. So G of equilibrium mixture minus G of 2 moles of NO2, right? So G of equilibrium mixture is 0. So let us calculate G for 2 moles of NO2 from the graph. So from the graph, you can see the value of, so this is the 0. And G of 2 moles of NO2 is this. This is the value. And this value is 5.4. Okay, so this plus this, 5.4 plus 0.84. Okay, so 0 minus 5.84 plus 5.4 plus 0.84. Okay, so this comes out to be minus 6.24 kilojoules. Okay, so therefore yes, this statement is correct. So therefore the answer will be D and E are the correct statements. Okay, so always remember, whenever you have a reversible reaction, the reaction does not reach completion. If we start from some amount of N2O4, it will become into an equilibrium mixture consisting of N2O4 as well as NO2. Okay, so whenever we calculate delta RG of the reaction, we assume that N2O4 has completely dissociated to form NO2, and therefore the delta RG naught does not represent what's actually happening. So we have to understand, in an equilibrium reaction, delta RG naught does not tell us the whole picture. Okay, thank you.